morning, everybody. Welcome back to Galois Theory. So first things first, I apologize for missing class Tuesday. I woke up Tuesday morning, and I say woke up after having slept maybe an hour and a half that night.
Oh.
And with a big headache, I decided, this is going to be my day off for the semester. Because I need it. Feeling a lot better today. Homework 5. Now due Tuesday after break. Because I want to do one more example today of finding minimal polynomials to give you some tips that might help you on the so today we're going to talk about minimal polynomials. We're going to talk about algebraic extension. But we're also going to talk about, by request, what are Dr. Gerstel's thoughts on all the math department offerings for the fall and summer?
Yes.
Which applies to some of you, not so much. Got my usual office hours this afternoon, 1 to 2, tomorrow morning at 11. All right, so stop me at any point. I listed all the courses that Math and CMP are offering for the summer and fall. So, other than the ones that you all have no business taking.
Are we able to take those ones anyway?
No. Yes, but no.
Don't go to the 105 course, Joe. Oh gosh.
I guess you could do 105 with summer of Murphy, but just why? Okay, so the summer, I actually have 4 math courses instead of the usual 2 that you all can take. Discrete math. As taught by Dr. Cipher.
Oh.
So he'll probably focus a little bit less on some of the more theoretical aspects of math and more on properties like trees, graph theory, algorithms a little bit. So he'll have a slightly different taste from how discrete math's been taught in the past, but still go over a lot of the same stuff, like how do you write a proof? How do you do induction type stuff? How do you set theory? A lot of which, if you're in this class, you've already seen, but there's still some good stuff in there that I think might be worth considering. Game theory every summer. If we're choosing business strategies, me and Eleanor, and we're going to business against each other, how do we choose strategies, keeping in mind what the other person's going to do that'll maximize our own profits? Say what?
Non-zero sum game?
Well, sometimes it's a zero-sum game.
True.
Sometimes it's just like, hey, that's some nice money. It'd be a shame if I took it from you. So I don't know if this is going to be offered how often in the summer this is going to be offered going forward. But discrete math is offered once a year. That's the plan going forward in the department. Game theory, offered every 2 years in the regular semester in theory. In practice, it's been 3 years, and it'll probably be at least another year or 2. So at this point, if you want to take game theory, you should take it over the summer.
It was fun over the summer.
Yay! I've taught it, but only in the regular semester. It's a fun class. Complex analysis. That one's me. I teach that every summer.
Sorry, who's the game theory?
Game theory is Troll. Yeah. Discrete cipher. Complex is me. That's it's like multivariable calculus, but and Calc 1 and Calc 2, and a little bit of pre-calc, but all regarding complex functions. So how do we integrate a complex function? How do we differentiate? How do we do series with complex functions? What do all these crazy things tell us? Most relevant to our class, how do we know that every complex polynomial, every non-constant complex polynomial factors into linear terms? We are not proving that in this class. We prove that in complex analysis. It's a good course, especially if you're thinking any sort of graduate school might be in your horizon. Complex analysis is a good one to have. And finally, numerical analysis, being offered in the summer for the first time ever. As a note, numerical analysis usually offered in the fall. It will not be offered this fall. It will be offered next spring, and it will be offered this summer, but not this fall. The reason? We don't have anyone to teach it this fall. Dr. Webster is going on sabbatical. And so Dr. Volshoff's going to be teaching a summer section of it. Much more applied course, numerical approximations and whatnot, required for the applied math major. So yeah, I've never taught it, never taken it, can't say too much about it. It has a reputation for being hard. Any questions about summer classes? Or move on to fall classes?
They're all summer session 1, right?
These are all summer session 1, yes. Unless you want to take Calc 2 with Dr. Gabler in summer session 2.
That would not be helpful.
That's what I thought.
It might be interesting.
It might be.
Oh, definitely interesting, but you don't do it. All right, fall. A lot of math, a lot of CMP. I didn't list all the math courses again for both summer and fall that I think you have no business taking. So, the calc sequence, for instance. If you're in here, don't take Math 105. You've got better things to do. Take non-Euclidean geometry if you want, like the math major version of 105.
Won't get off. When was that?
Probably a couple years. So, math logic.
Well, not
Math logic. How often is that offered? Once every 2 years.
in quotation marks.
Because that one has become more of a 3 years, if that. That one, so that's looking at the theory of theories, is the way Dr. Gabler likes to describe it, and that's a Gabler class. That's pretty much a Gabler exclusive. I think he's the only one in the department who really teaches that one. Not because it's not a fun subject, but because it is very esoteric and out there. But mathematical logic is arguably the purest of the pure math courses. Those of you who are interested in such things, Eleanor, I thought that might get your attention. In terms of like high-level theory. Gets into things like Gödel's incompleteness theorem, I think is kind of the end goal of the semester. Probably your all's last chance to take it if you're going to take it, I'd say. Differential equations is it's been a spring course for faculty reasons. It's being offered in the fall this time instead of in the spring. Yeah, advanced calculus uses some good tools from linear algebra with like eigenvalues, eigenvectors, bases, and stuff. Differential equations, great one to have under your belt if you're thinking grad school in the future, pure or applied. Keep that in mind. Probability.
Who's teaching that?
Oh, yeah, sorry. Trelaw. Probability. Being taught by not Trelaw for the first time in like a decade. Maybe like 5 or 6 years. Probability. Being taught by Hutchinson. That's every fall. Good applied math course. Nice solid learns probability theory. I will note for probability that there is going to be a follow-up spring course, mathematical statistics, that will have probability as a prereq. That will probably also be taught by Hutchinson. So keep that in mind. Complex analysis. Once every 2 years. Plus every summer. Gabler's going to be teaching it in the fall. If you want to take it as a 15-week course. 15-week course instead of a 3-week course with me. Cryptography. Topics course.
What's the prereq?
This is your only chance. Cryptography, that's me. Prereq, linear algebra, you all can take it.
Hey.
Even if you haven't had linear algebra, I will give any of you all permission to take it.
Linear algebra for no one.
Which has abstract algebra as a prereq, which has linear algebra as a prereq, I mean. But yeah, cryptography, breaking codes. Look at sort of the history of how as coding theory and cryptography proper developed over time. Involved a fair bit of number theory, which I'll have to sort of learn over the summer.
I need to be here for that.
Probably get to the computer lab some days to do a little bit of playing around with like RSA, elliptic curves, and such. Promises to be a fun time. my first time doing an applied topics course. How exciting. Yes. Exciting. Teaching secondary math. I'm just gonna put this is probably your only chance. That's another one I'm teaching. That's gonna be a 1-credit course.
Last time it was taught was my only chance and I missed it.
I'd say that was probably with John and Greg, right?
No, it was with you. It was like
It was definitely not with me because I've never taught it.
wait. Oh, this is a different one. Class then.
Secondary math. Yeah, I taught an elementary version a couple years ago.
What was the one I missed then?
Secondary math, is high school math. Yeah, we just sit around and kind of have a bunch of discussions about what it's like to teach a class. What sorts of issues do you run into teaching at like the high school level, and a lot of it will be generalizable. And I would all have to poll the students, but last time I went into teaching elementary math with the idea of it being like half theory of education, half practical advice, and the whole thing ended up pretty much being practical advice by student demand. And plus, because there were like 6 students teaching at Will Carleton over at the time. Depending on what the students who take sign up for the course are interested in, I'll try and mix in some like theory of like, why do we educate? What is the good in education? Get into, and then also talk about what are my thoughts on like how do I structure a class? How do I put together like an exam, stuff like that. How do you deal with parents? Something that most college professors, but I do have to deal with.
So have you spent time teaching elementary or?
Nope. I've tutored in elementary schools and high schools before.
And you certainly spent time.
When I taught the teaching elementary math, my mom's an elementary school math teacher, so I got a lot of tips from her. She in fact came in and gave a guest lecture.
We kind of act like high schoolers. So I think it's
Well, basically, no, you're right. I've basically taught high school. Slightly more advanced math than what you typically get at high school, unless your name is Andrew Schmidt. But high school mentality of high schoolers, nonetheless. Yeah, this is not a regularly offered course. It will be offered again, but probably not until you all have graduated. Andrew, small chance you'll still be around.
I wish I could take that class before applying for the teaching jobs I'm applying for right now.
Yeah, well, meaner. Should have thought of that sooner.
That absolutely would have helped the class that I don't think was offered while I was here.
Okay, so any questions about the math courses for the fall?
So last semester, someone had asked for your ratings by difficulty from what was the scale?
Multivariable calculus to abstract algebra.
Right, where multivariable calculus. Right.
I still didn't like that rating system. I still don't like that rating system.
To me, that's a negative. Like.
Well, aren't you special?
Well, no, multivariable.
How about I give them all a score from 1 to 5 in terms of how difficult I think it'll be? Does that sound good?
Sure, but also, could you give a separate score for how cool you think they are?
Sure. All right, difficulty ratings 1 to 5.
1 to 6. And
Difficulty, shut up, I'm not doing it at all. 1 to 5.
You're not allowed to use it.
I enjoy
4. 2 to 3. 2 to 3. 3 to 4. 3. 1.
Would you put Galois theory at?
4.
I enjoy how every time I've had
Dr. Gabler, would you care to say anything to the contrary?
He doesn't want to talk at the moment.
I know, that's a dead joke. I'm just being mean to him.
Every time that we've done one of this that I've been in class, I've been in a slightly more advanced class, and every time there's fewer sections you write on the board.
Well, I mean, you all are like, this is like the most advanced math course this department offers. So, like, of course it's going to be like that. All right. How cool do I think it on a scale of 1 to 5? 4. 3. 2. 4. 4. I mean, I don't know how to rate that one. If you're interested in teaching 5, if you're not interested in teaching 1, I mean, like that's like very much like a.
You didn't rate your own
And what do you
class
rate
a
down
five.
law exactly?
What about summer courses?
Difficulty 2, 4, 5.
Oh.
How interesting do I? If I know my Dr. Volasov and how many students I've seen it outside her office hours for numerical analysis, how interesting do I think they would be? 2 to 3. 3, 4. I'm not answering. And discrete math, the only reason I said 2 to 3 is for you all, a lot of it would be stuff you've seen before, like how do you write like a basic proof, how do you do basic set theory, like the new stuff I think would be very interesting, but a fair bit of it would be review. Just to be clear.
That makes a lot of sense.
All right, so if you all haven't heard, Dr. Oliver Sarang will be coming to teach at Hillsdale this fall, so we'll have 2 computer scientists.
We've doubled the department.
The sub-departments.
The sub-department.
So that's why there's 6 computer science courses being offered.
How many until it's a major?
2 of them are CMP 101, which is why there's only 5 listed. I'm not answering that. Yeah, so Sarang, Cipher. Intro CS.
No, actually, algorithms is Sarang.
Yeah.
And
That's.
Oh, that's.
and data structures is.
Oh, I thought that was
No.
Steve for Cipher. Oh, well, okay. Well, maybe I'm wrong.
He gave the rundown yesterday.
Oh, well, then I would trust him over me.
Yeah.
He
Both
wrote,
intros are Sarang.
he wrote the initials, so S next to each.
Oh, yeah.
Nice.
Yeah, if you want to take, yeah, this is being offered by an operating system. This one's being offered by a
JavaScript.
He just wrote this.
okay. Okay, but yeah, basically, what I'll say is, thanks, yes, courses. In all seriousness, though, anyone who's wants to get into any sort of like mathematical technical field after graduating, having at least one computer science, like at least the intro course under your belt would be super helpful. Something that like you can use to help you get jobs. Just so much of what we do in modern world is computing based that actually having ACS course can definitely help open doors for you. So pure or applied, no matter pretty much if you want anything math-ish. Yeah.
Unless you just teach and then it doesn't matter.
Dr. Gerstel, why is discrete math 335 equal to CMP 202 logic and computing computational structures? Because we're trying to get a new course numbering for it, and I think that will be able to apply for the fall, but not the summer. It'll be the same course, well, other than the fact that one's compressed into 3 weeks. Both are being taught by Cipher. Both of them are discrete math.
Oh.
Cipher wants to be crazy though and be sneaky about it by tricking students who've taken discrete math to sign up for it. I don't know. One thing I will note for CMP is cryptography. I've asked Dr. Cipher, and he said you can count that towards the CS minor instead of a math major should you so choose. No, you're not allowed to double dip.
For me to wish I could stay another year. I could
All right. How often? I'm not going to answer how often each of these are offered, other than to say intro will continue to be offered every semester, because having a second faculty member changes things, and I'm not sure how. I'm not sure if Dr. Seifert knows how exactly for some of these. I will say this will be continued to offer every semester. There will continue to be some sort of discrete math course offered every year. No, I don't know if we're going to be offering discrete math 335 in the spring. This is probably not going to be a regularly offered course, but as far as data structures and algorithms, I'm not exactly sure. Ask Cipher. Any questions, comments about any of these? No, I can't give you difficulty and interest ratings for all of these.
So if we were not to take complex analysis this coming fall, it will still be offered over the summers?
Yes, I plan to continue offering it every summer as long as I can get at least like 3 students. So this will be offered in the fall, and then won't be offered as a regular semester offering for another 2 years. So, Eleanor, you're sophomore. So for you, if you didn't take it this fall, you would have to take it in the summer at some point.
There's no way.
In fact, the only one who can take it in the fall or who can skip it this fall and have another chance to take it in regular semester is him.
That is correct. Matthew.
Is there like senior capstone offered at?
Oh yeah, senior capstone. Forgot about that. Yeah, if you're a senior, there's CMP 450. It's being taught by Murphy this fall. I don't know who's doing it in the spring.
See?
It's a CMP or COR, not CMP. Yep, one of those C courses.
Yeah.
Yeah, Dr. Seifert's doing capstone. That would be terrifying. COR 450. Yes, senior capstone will be offered in the fall and spring. Required for all majors. If you're a double major, you only need to do one capstone course.
Oh.
So if you're doubling majoring in like math or physics, if you want to just do the physics capstone, that's totally fine.
Oh.
Is that class a 1 credit and like what do you?
That is a 1 credit class. So it's 50%. You go to lectures with Dr. Arn, where he talks about
Propaganda. Okay.
I'm not going to comment. He talks about whatever he wants to talk about. And then it's like six meetings with the class where basically, like, there's like some assigned readings. You kind of sit around and talk about them, like talk about like what is the role of math in the modern world, type stuff.
What is the good? What does the math mean? Why don't we integrate when we could, go into society?
Do you get difficulty and interest rate?
I did not hear any of what you just said overall. This
He wants a difficulty and interest rate.
Oh, for capstones, difficulty 1, interest rating.
Required.
-1.
Interest rating, it doesn't matter, you're taking it anyway.
For those who don't want to graduate.
Let me put it this way. There's a reason why Dr. Murphy's usually the one teaching it, not anybody else in the department.
Oh.
Not because it's not fun. I've taught it, and I actually had a good time with it. I would have offered to teach it this fall, actually, if I wasn't already doing this as a extra 1 credit. Yeah, it's like, it's just, I don't know, it's a capstone. It's required. The ARN lectures are the same no matter what major it is. But know that you will have to write a paper based off the ARN lectures, responding to some questions, and that will be graded by whichever professor you take the capstone from. So Dr. Murphy, if you do it in math, for instance.
And you have to write a second paper about the math part too.
What's the percent chance his wife reads it?
Greater than 0.
What if he does actually grade papers though?
No, he'll actually do it.
History and math.
He's like the one of us in the department who actually knows like how to grade a paper.
That would
Do you
explain
wanna
why he does
You do want to
science
take the
CSS.
capstone outside.
Yeah.
It's like
I don't
the
think he's.
only one.
Well, actually, now that there's 2
Person
CS
I've
people,
seen
he
that's
might
CS.
teach at some point. Like, I can see him wanting to. I don't know. Okay.
The physics department is
Alright.
peace.
All right. In all seriousness, though, before this class gets completely derailed, any other questions about course offerings coming up? Let's do some algebra then.
Wait, no, what about the joke of the day?
Yeah, I've had enough jokes from you.
But you have to make a
Knock knock.
Who's
joke.
there?
Who's there?
Parker's failing this class. Anyway.
That's a joke!
That's a good joke.
You can't just say that. It's like one of the 2 classes I have a.
You literally demanded it from me, Parker.
That's one of the key classes.
All right. So, let's get back into some actual Galois theory. I know it's been a week. I know you all want to goof off. I know it's Thursday before spring break, but come on, let's do this. Big snazzy big theorem. We're letting L be a field, K be a subfield of L, alpha being some element in L, may or may not itself be an element in K. And we're talking about what does it mean to take the minimum polynomial of K. So last time we kind of got halfway through proving this. We showed that if alpha is the root of some polynomial in K, or if alpha is not a root of any polynomial in K, then the field extension generated by alpha over K, meaning the smallest field that contains both all of K as well as alpha, is going to be isomorphic to just the field of rational forms over K. Think field where you're taking polynomial in K divided by polynomial in K. If alpha is not a root of any non-constant polynomial in K. If alpha is the root of some non-constant polynomial, then we say there exists a unique, monic, irreducible polynomial such that for all functions, all polynomials over K, f of alpha is 0 if and only if this m is a divisor of f, that the field of rational forms over, or the field extension of alpha, of K over alpha, is equal to the polynomial ring of K with alpha. And finally, the degree of that field extension is equal to just the degree of the minimal polynomial. Hence why we're using the word degree and not like dimension, for instance, when we talk about like field extensions. Yes, James?
So the parentheses thing is called the field extension then?
Yes.
Cool.
Field extension of K with alpha. Basically, think of this as being, we kind of talked about this last Thursday, or last class, but think of this as being the smallest field that contains K and alpha. This is the smallest ring that contains K and alpha. Meaning, this thing just has to have polynomials of alpha, it doesn't have to have quotients of polynomials of alpha necessarily, unless alpha is a root of some non-constant polynomial. And that polynomial we call m. So, for instance, let's do a quick example. Let's say our field extension is looking at the rationals, and we're going to extend to include square root of 3 and square root of 5. And I'm interested in finding the minimal polynomial of alpha equals square root of 3 plus square root of 5. This is just an example before we jump back into our proof, because it's been a while since we talked about this. So in other words, I want to find some polynomial that is irreducible and that's monic. Monic meaning leading coefficient is 1, for which alpha is going to be a root. And I want the degree of that polynomial to be equal to the degree of this field extension. So, question, what is the degree of this field extension? Lincoln?
4.
Why?
You need a plus b root 3 plus c root 5 plus d root 3 root 5.
Yeah, essentially. Basically, we could say that like the degree of the extension of just adjoining square root of 3 over q is 2. We've kind of seen this one a few times now. Why? Because this is just the set of all elements of the form a plus b square root of 3, a and b are rational. 1 comma square root of 3 forms the basis for that as a Q vector space. And the degree of this field extension is also going to be 2. Why? It's not going to be 1 because these are not equal. This contains more elements than this does. Specifically, square root of 5 is in this ring, but not in that ring. Or in field, I should say. But we know that elements in here are the form a plus b squared root of 3 plus, it's degree 2 extension. There's adding square root of 5 adds like one mix for like twice as many elements, essentially. And so we've already proven as a theorem that this times this should give us that. So 2 times 2 is 4. So we're looking for a degree 4 polynomial over Q for which this thing is a root. How do we find such a beast? James?
Well, we take the expansion of x minus the square root of 3 plus the square root of 5 times x minus the square root of 3 minus the square root of 5 plus times the x plus the square root of 3 plus
Oh,
the
that
square
sounds
root
so
of 5
messy. I don't
plus-
want to do that. I'm going to show you all the trick. And yes, you can do something similar in the homework.
Oh.
We're going to square both sides of this.
Oh. What? Oh, honey.
No.
This one gets messy.
Jackson. If we were to FOIL this out, what would we get?
3 plus, oh yeah.
3 plus 5. I'm just going to skip straight to the simplified
Okay,
version.
yeah. And then, plus 15 it looks like, 'cause it's, well, wait, hold on, so it's the square, 2 to the, 2 square root of 15.
Yep, plus 2 square root of 15. Y'all ready for this? I'm going to subtract 8 from both sides.
No way.
Oh.
Oh my science.
Oh my.
Oh, and you could swear that.
And then we're going to square both sides again.
Oh.
Oh.
So on the left-hand side, we'll get alpha to the 4th minus 16 alpha plus 64 is equal to, Isabel, what do we get when we square 2 square root of 15?
60?
We get 4 times 15 is 60.
Oh my science. Whoa.
I'm going to subtract 60 from both sides, and we're going to get alpha to the 4th minus 16 alpha.
Alpha squared.
Oh yeah, good call. Yeah, because we're subtracting 8 alpha squared minus 8 alpha squared. Plus 4 is equal to 0. With that in mind, can anybody think of a degree 4 polynomial that is monic for which over Q for which alpha is a root?
Alpha to the 4th minus 16 alpha squared plus
I wanted something in terms of x.
x to the 4th minus 16x squared plus 4.
How did you come up with those?
Magic.
God.
So there, that's one way to find irreducible polynomials when you have these sort of nice square root extensions.
You could take conjugates as well.
You can do it with conjugates, but then it just gets messier. Algebraically. And it should multiply out to give the same result though.
It multiplies to the same result, but it is messy.
So that's one way you could actually find a minimal polynomial over Q, for instance. And we know it's, how do we know this thing is irreducible? Hint, you can't say Eisenstein because Eisenstein
Oh.
4 is not prime.
Yeah. No.
Well, wasn't it just based off of the construction? Or actually, no, because you could argue that maybe there's a way we could reduce
Yeah,
this.
how do we know there's not a degree 2 or a degree 3 polynomial that alpha isn't a root of?
Because then we could write all of the, like if we had a degree 3, we could write x cubed and x all the higher powers in terms of the smaller terms.
Essentially, it's because homework 5, question number 3.
Yeah.
Turns out if you know that if alpha is a root of some polynomial that happens to have the same degree as the minimal polynomial, if you happen to know what the degree of the minimal polynomial is through other means, like how we already found it should be degree 4 earlier, then that means it automatically has to be irreducible.
And we will prove it in the homework.
And you will prove that in the homework. Not that hard.
I feel like I'm missing something still with the
I am also
that I
missing
have, but
Andrew?
Could we also say if the smallest also say?
Could we also say the
for
small
something-
things?
For some, if the degree is less than twice the degree of the field extension, we still say it's irreducible. Because otherwise there'd have to be something of degree, a factor of degree less than.
It's less than twice the degree of the extension in that. Yes, you could. Slightly trickier to prove, but you could show that case. Okay, so you just take irreducible squared, or minimal polynomial squared. Note that if alpha is a root of it, and it's the same degree as the minimal polynomial, that doesn't necessarily guarantee it is. Your polynomial is the minimal polynomial, because there's no guarantee that your polynomial has to be monic. But it does have to be a unit multiple of the minimal polynomial in that case. Any questions before we continue our proof of BSBT? All right, in that case, last time we proved part 1, we proved part A. Things we still need to prove. This part, this part, this part, this part. All right, so, back. So last time you may recall that we defined the minimal polynomial. M of x is going to be the polynomial of smallest degree non-constant before Jordan reminds me of smallest degree for which alpha is a root in K. And the minimality of the degree of this thing is going to be important for proving, well, it was important for proving part A already, but it's also going to be important for proving some of the later parts of this proof as well. But that's how we originally defined M. We just said, take all polynomials for which alpha is a root in K, pick one of minimal degree, call it M. And then we also said, without loss of generality, M is monic, because if M isn't monic, then just divide by the leading coefficient and take that instead. So we still need to prove that this M we found is unique, satisfying these conditions. It's irreducible, and it has those things as well. And what I'm going to start with is uniqueness. So let's prove that M is unique. And specifically, what we're going to do is we're going to use condition A here. We already proved that condition A has to hold for this thing up here. We did it without using any properties of uniqueness or anything, or irreducibility for that matter. So it turns out part A here is what gives us the uniqueness. So we're going to suppose that M prime is another polynomial of minimal degree with alpha as a root. Polynomial in K of minimal degree with alpha as a root. And we need to show that M prime has to be M. That there's not some other polynomial out there that can do that. Well, I hinted at the fact that we're going to use condition A. So we can then say, by condition A, what do we know about the relationship between M and M prime? If M is a polynomial where alpha is a root, and M prime is a polynomial for which alpha is a root,
M divides M prime.
we know that M has to divide M prime. Because any polynomial with alpha as a root, M has to divide.
Then we can switch.
But we also know that if M prime still satisfies the same minimality condition by the same argument we did in part A, we know that M prime has to divide M. And if m divides m prime and m prime divides m, what does that tell us about the relationship between m and m prime? They're unit multiples of each other. Thus, m prime is equal to u and m for some unit u an element in k. Also, I forgot to include the word monic here, and that's kind of important.
Oh, well, yeah, but even if it wasn't monic, you can just say that if you.
Well, then m and m prime are not necessarily equal if we don't require monic.
Yes. But they're.
Because I could just say herp and derp, here's another minimal polynomial,
Yeah.
otherwise, if we didn't require that monic condition.
If it's a unit multiple though, then doesn't that mean it might not be monic? So.
Sure, but if we also require m prime to be monic,
Then they're just equal.
then they have to be equal, yeah. But since m and m prime are monic, we know u equals 1, hence m prime equals n. Since they have to have the same leading coefficient, and one's a constant multiple of the other, the only way that can happen is if that constant happens to be 1, then you have the exact same polynomial. Any questions or comments about uniqueness property? Seeing none, I will put a check mark. All opposed? Seeing none, the motion passes. That's how in faculty meetings we vote on things, by the way. It's like any opposition, Dr. Kalthoff will say all opposed? Hearing none, the motion passes. With that amount of pause right there. Alright.
I haven't decided if I'm going to oppose that yet or not.
Well, usually that's after we've had a minute of discussion about something.
So if you have an objection, as soon as they say the motion, you gotta.
Pretty much.
Interrupt them.
How dare you!
Let's do irreducibility next. So the next thing we need to do is we need to show that m has to be irreducible. So we're going to do a proof by contradiction here. We're going to assume that m is reducible and show if something bad happens. So let's suppose m is equal to, I don't know, some pq, some p and q in polynomials over k, with both having degrees strictly smaller than m. So in other words, we're assuming m is reducible to start, and we're going to prove something bad happens. So how do we prove something, how do we show something bad can happen? Well, if m is equal to p times q, or if you prefer, m of x equals p of x times q of x, what can we plug in for x on both sides of that equation and have things simplify nicely?
Alpha.
Let's plug in alpha. Because what is m of alpha? If alpha is a root of m, what is it? What do we get when we plug alpha into the function m, Matthew?
0.
We get 0. Which tells us what? That since all fields are integral domains, if p of alpha times q of alpha, since those are just elements in K, if that product comes out to 0,
One of them is. Or, well, yeah.
p of alpha equals 0, or q of alpha equals 0. Which means
It's no longer zero.
which means we have a polynomial of degree smaller than m for which alpha is a root. And that is no good. Contradicting the minimality of m as such a polynomial. Having this property. That alpha's a root. And that gives us irreducibility. Because if it was reducible, then we'd be able to get a polynomial of strictly smaller degree that has alpha as a root. And if we assume m is already the polynomial of smallest degree, a polynomial of smallest degree satisfying that, then that can't happen. Questions, comments? Well, pop. Alright, so that just leaves us with parts B and C to still prove. We've proven that m is unique monic irreducible polynomial that satisfies condition A. If it satisfies condition A, that gave us the uniqueness part. And next thing we're going to do is we're going to prove part B. So we need to show that the smallest field containing k and alpha is equal to the smallest ring containing k and alpha. One of these, there's no work to do. We're going to prove each is a subset of the other. One direction of that, there's no work to do. Which one of these is a subset of the other automatically, no matter what your alpha is? Lincoln?
Backwards direction.
Yeah. We know that this is something that's going to be true for all alpha. Because this is just polynomials of alpha and k. This is quotients of polynomials of alpha in k. This is made up of the quotients of elements of this. So you can just take anything in here, divide by 1, boom, you have a quotient of things in here. So in order to prove equality, what we're really going to need to do is to prove that the left-hand side is a subset of the right-hand side. So in other words, what we're going to do is we're going to let f of alpha divided by g of alpha be elements of k of alpha, the field extension, where g of alpha is non-zero, because if g of alpha was 0, then bad times would roll. Meaning we'd be dividing by 0 and don't divide by 0. And our goal is going to be to show that f of alpha over g of alpha is just some polynomial in alpha. Y'all ready for this? I like this proof. This is a sneaky rule. By part A, we know since g of alpha is non-zero, we know that m does not divide g. Because if m divided g, then well, g of alpha would have to be 0, by the if and only if part. So g is not a multiple of m. We also know now that m is irreducible because we proved that. So with that in mind, what's the GCD of m and g? Yeah, they can't have any common factors or any non-constant factors in common with each other, because otherwise either m would have to have a common factor, or m would have to have a proper divisor, or m would have to be the GCD. But if m is the GCD, that means m would have to divide g. So in other words, this is going to force that the GCD of m of x and g of x is going to be 1. And yes, I say the GCD, I mean a GCD, because technically any constant unit multiple of 1 would also work. Is that where you're going to say, Lincoln?
Yeah, well, I was only going to say -1 specifically, but yeah.
Oh, well, yeah, okay. Basically, any non-zero element in K would fit the bill here. So now, I'm going to go to a theorem that we haven't formally proven, but we've used before. Those of you who had me in 410, we've used. But which basically says if the GCD can always be written as a linear combination of the two elements. That's kind of a well-known like number theory property. So I'm going to say thus, there exist A of x and B of x in the polynomial ring K of x, such that A of x, M of x, or no, A of x, G of x, plus B of x, M of x is equal to 1. That's just kind of using the property that the GCD can always be written as a linear combination of the two elements. Yes, Jonah?
Wait, so I guess it's clear to me that that works for like ordinary numbers and so on, but like
It works
is that
over any
true
Euclidean domain.
Okay.
And as we've seen, polynomial ring over any field is always a Euclidean domain. That was one of those big nasty theorems we proved several weeks ago. So yeah, the reason why it works over any Euclidean domain is basically because you just do Euclidean algorithm backwards. That's how it works over like the integers, and just apply the same process, but slightly messier looking with, since you're dealing with polynomials to get for over polynomial ring over field. All right, we got this nice equation here with in terms of x. I'm going to plug something into x on both sides of this equation that'll make the left-hand side simplify a little bit.
Alpha.
Let's plug in alpha. So, what do you get if you plug in alpha into the right side of the equation? Oh gosh, I got all choked up thinking about it.
Oh, 1.
Yeah, what do you get when you plug in alpha for x here? There is no x, so you just get 1. So I'll just say plugging in alpha for x gives 1 is equal to A of alpha, G of alpha, plus B of alpha, M of alpha. And what can we swoosh?
B of alpha and alpha,
Why?
because M of alpha is 0.
Oh, hey, this term is 0. So that goes bye-bye. So that tells us, what does that tell us? Well, that tells us that G of alpha is equal to 1 over A of alpha.
Whoa.
Whoa, what?
So we can rearrange them so that A of alpha equals 1 over 2. Or just multiply by it, yeah.
Which tells us our original element in the field extension of K with respect to alpha also has to be an element in this polynomial ring.
So we proved that there is some element, because we're plugging in alpha. Never mind. Nope, just kidding. Makes sense. I was thinking K adjoint X.
Yeah.
Which gets more complicated, but it's K adjoint alpha, so it's fine.
And where the proof would fall apart in like case 1, where there is no f of x such that alpha is a root, is because we used.
Well, where the proof would fall apart is M, there would be no M. Yeah, like the existence of M comes from the fact that we're not in case 1 where there is no polynomial. If there is no polynomial, then you can't take the thing of minimal degree among things that don't exist at all. I mean, I guess you can. I mean, you can, but then it's just,
Doesn't really exist.
then does it really exist? So that gives us party. That shows that every element in here is also an element in here, and since the reverse inclusion is pretty clear, they're So the last thing we need to do is to show that the degree of this field extension is equal to the degree of the minimal polynomial. Sound good? Which means we need to find ourselves a basis. Is everyone okay with this? Can I erase? Seeing no objections, the motion carries. Like Dr. Kalthoff, I'll actually give you all the chance to object. So part C is probably the most interesting part of this theorem, because what part C is going to give us is kind of a nicer way to tell what is the degree of your field extension. Instead of having to look at forming a basis of some vector space, you just find the minimal polynomial and take its degree. It's a little bit nicer in a lot of cases. So the way we're going to do that is we're going to construct a basis. So with that, we're going to start by saying suppose that the degree of our minimal polynomial is some value n. We know n is greater than 0 because m of x is non-constant. We established that like back when we originally defined m. So I want to find a basis with n elements in it for k of alpha as a k vector space. So what would be n elements that would be linearly independent and also span all of k of alpha?
Well, especially since we already have B over there. We can just do 1 and the minimal polynomial to the 1 and the minimal basically linear combination
Of the minimal
of
polynomial?
the minimal polynomial to everything up to n.
I have a slight issue with that. Minimal polynomial is a polynomial in terms of x, right? Is that an element of this thing?
But we can just plug in. Wait, so it's
Oh, the minimal polynomial where you plug in alpha for x?
so no,
Yeah.
okay, so just make the polynomial, so just do 1 alpha squared, and so.
That's what I'm looking for. Turns out that's going to be a basis for k of alpha as a k vector space. Now, you can't really use the minimal polynomial here itself.
Yeah.
I mean, we're going to use properties of it to prove that this is a basis, but if you just try to take the minimal polynomial and plug in alpha, you just get 0. So yeah, that wouldn't be super helpful. Pro tip, don't let 0 be a basis element. You're going to have a bad time. Unless you're looking at a 0-dimensional vector space. So, we need to prove 2 things. Like I said, big snazzy theorem, a lot of different substeps.
Wait, what happens if we do choose alpha as 0? Like what?
Is with 0?
Yeah.
Then we get, if 0 is a basis element, you're automatically going to get non-linearly independent. Because there exists a non-trivial linear combination. So if we had 0 in here, we could say, I can give you a non-trivial linear combination of these things to get 0. Make 0 times 1 plus ... plus 0 times alpha to the n minus 1 plus 27 times 0. Oh no, a non-trivial linear combination that results in 0.
What happens for the rest of the theorem?
Well, 0 is going to be in your, like, if you were
If-
to not
What's going to happen for the rest of the theorem if you do what? Include 0 as a...
Right, we had 0. Oh no, 0 is already going to be in. Okay, then it's okay.
But what if alpha is itself 0?
Then if alpha itself is 0, then the minimal polynomial...
Yeah.
Then the minimal polynomial is x,
Yeah.
and it's a degree 1 extension.
Okay. So the basis would just be 1.
You still have
Yeah.
out of the.
Right.
The basis would
so
just
it's
consist of
still-
1.
Okay, so it still works.
Notice that I specifically stop at alpha to the n minus 1, because if we went to alpha to the n, we would be able to get non-linearly independent. We would be able to get a linear dependence relation using the minimal polynomial.
Or you can leave out 1.
If you left out 1, yeah,
And do it.
if it had alpha, then that worked.
If you leave out 1 and include alpha to the n, then it would still work, yes.
Nice little cyclic thing.
It is. In fact, pick any n consecutive powers of alpha, and you could get the job done.
Start at 5 if you want.
So,
I'm not going to do that for this proof, but you could if you really wanted to, Isaac.
so is that just a way of saying that alpha to the n is a unit?
It's a way of saying alpha to the n is a linear combination of the things that come before it in k. Let's write some of this down so we can sort of see. Eleanor, since you asked, you want to start with showing this spans k of alpha, or do you want to start by proving it's linearly independent? Let's do linearly independent. Why am I looking at my 105 notes?
I don't know, why are you looking at your one?
Because I don't know the difference anymore. So let's start with linearly independent. So how do you show a set of elements is linearly independent? You set them all equal to 0. No. I'm ashamed to call myself your linear algebra prof. Now you take an arbitrary linear combination of them, set that linear combination equal to 0, and then show that all the coefficients have to be 0.
That's what I was saying.
No, it wasn't.
That is not
That
what
is
you
not what
said.
you said.
That is not what you said.
That's not
All right,
what it
guys,
said, but
calm
that
down.
is what it-
Let's suppose for some elements a sub I and k that we have that a sub n minus 1 times alpha to the n minus 1 plus a sub n minus 2 times alpha to the n minus 2 plus a sub 1 alpha plus a naught is 0. So we're going to suppose that we have some linear combination of, and we'll call this S, elements of S that gives us 0. And we need to show that all the coefficients, all the a sub I, have to themselves be 0. Well, we somehow need to get the minimal polynomial involved here. So what I'm going to do is I'm going to define a new polynomial. I call it f of x. And I'm going to define it to be, I don't know, a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus a sub 1 x plus a naught. And what do we know about this polynomial? Lincoln?
It doesn't have a root at alpha unless it's,
Doesn't have a root of alpha?
sorry,
I very specifically constructed it so that f of alpha is 0.
oh,
And I replace all the alphas with x's.
right.
So this has alpha as a root.
So it must be the minimal polynomial.
No.
We have,
Shame
we
on
have
us.
multiple of them, or
What?
m divides it.
Well, hold on. Minimal polynomial is the polynomial of minimal, non-constant polynomial of minimal degree satisfying this. What's the degree of f of x? Or less.
Yeah.
Because
Less than.
I mean, if this,
Um,
it could theoretically it's this 0, this non-zero.
It's less than n.
It's strictly
Problem.
smaller than n, which is the degree of the minimal polynomial, which is a problem unless this polynomial is the 0 polynomial.
Oh. Therefore, it must be 0. And then like.
So I'll say contradicting the minimality of the degree of m unless a sub n minus 1 equals a sub n minus 2 equals a sub 1 equals a naught equals 0. Because, I mean, if this is a 0 polynomial, that's fine. 0 polynomial is always going to be a polynomial of smaller degree with alpha as a root. But the point is, m is the polynomial of minimal degree with alpha as a root among all non-constant polynomials. So if this is a, so let me say unless f of x is constant, and the only way for f of x to be a constant function and still satisfy all this is if that constant happens to be 0, meaning a sub n minus 1 equals a sub n minus 2 equals a 1 equals a naught equals 0. So that gives us linear independence. Everybody okay? Andrew, you look like you have something you're about to
I'm good.
Okay. All right, the final part of our theorem. We need to prove the spans K of alpha. And at this point, we can erase big snazzy here.
Maybe we're erasing the snazzy beat-em-up theorem.
Oh no.
The big snazzy behemoth theorem.
Wait,
Yeah.
K square alpha or K parentheses alpha?
They're the same because it's part B. So let's let P of alpha be some element in the polynomial ring K of alpha, which as we know is equal to this from part B.
Very much so.
And we need to show that P of alpha is in the span of S. Guess what it's time for again, kids? Okay, maybe this
Is
one.
I don't want to.
Is it- Oh gosh, I can't.
What are we going to use for the? What have we used about 10 times in various proofs this semester, and we're going to use it again?
What's algorithm?
The Euclidean algorithm. We're going to say then for some Q of alpha and R of alpha. What?
Nothing.
Okay. I know, isn't it so handy? Where the degree of R of alpha is less strictly smaller than the degree of M of alpha. We can write P of alpha as being equal to Q of alpha, M of alpha.
Should these be like Q of X's and R of X's?
No,
No, because we're looking at the polynomial ring of K over alpha, not polynomials of X. Well, what does that tell us? It tells us P of alpha is R of alpha, yay. This is equal to 0. P of alpha equals R of alpha, so the degree of, let's say, P of X, fine, Joan, I'll throw X in for you now, has to be strictly smaller than the degree of M of X. Why? Because P is equal to R and the degree of R of alpha is less than the degree of M of alpha. You're just replacing alphas with X's here. But the degree of M of X is N, hence P of X equals a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus a1x plus a naught for some elements a sub I coming from our base field, which in turn implies P of alpha has to be a sub n minus 1 x to the n, or alpha to the n minus 1 plus a1 alpha plus a naught. And wouldn't you know it, that's a linear combination of the elements of S. That's in the span of S. Turns out we only need the first n up to alpha to the n minus 1. And this, Jonah, would be kind of like where if you didn't start at 1 and go up to n minus 1, if you started at 5 and went up to n plus 4, doing this part of the proof would be annoying to work around.
It doesn't have to be consecutive.
It doesn't have to be
You
consecutive.
just choose things through the same mod. And
Yes, you could do like 1 alpha squared up to alpha to the n minus 1 and then alpha to the n plus 1. I think you could do, yes.
But why would you?
Well, there are reasons, but not for us in trying to prove this. Any questions or comments? Hey, how about that? We're basically done at this point. because now we know.
Just watching the chalk go poof, poof, poof.
I know, whoosh. So that tells us that this is a basis for K of alpha as K vector space. We've proven our claim. So if we want to look at the dimension of this field extension, that's just the number of elements in S. And Eleanor, how many elements are in this set? There's n of them. And wouldn't you know it, that's the degree of our minimal polynomial. Wow. You know, this is such a big proof. I'm gonna give it 2 boxes. Don't be ridiculous.
As the prophecy has foretold.
As the prophecy has foretold. Holy moly. Alright, and I think we'll call it there for today. So when we come back next Tuesday, we're gonna start looking at algebraic numbers versus transcendental numbers. And we might even use a little bit of cardinality, real analysis-y type arguments in order to prove that transcendental numbers exist.
I was looking at, I don't know what it was, maybe a random.
Oh, stop the video. Bye Lydia, hope you're doing well. Have a good spring break.